Testing, testing, testing. 1, 2, 3. Let's see if we have anybody. Kristen, we can always count on Kristen. She's there. Hello, Kristen. Earth call. Hey, there she is.
Yeah, it takes a second for my audio to connect, and I can't hear anything until it does. So,
Okay, well, we have the two of us so far.
yeah, just the two of us.
It's a little early.
Yeah, a little bit. Oh, I'm still trying to wake up. My coffee hasn't kicked in yet. But I have all my stuff, and I'm ready to go.
Yeah, I think I'm ready. Everything seems to be working.
Uh,
We're this is our last week. You know that.
yes, sir.
So we're going to have, all you got to do is listen to eight more lectures from me, Kristen.
Yeah, that's true. Yeah.
Eight more.
Yeah.
But right now we're dealing with dynamics. And I wanted you guys to work on F18.8. I've got a picture of it there. Let me see if you can see that. F18.8. Now let's see, I need to pin. Okay, pin video. There we go. I need to adjust this a little better. It's not too bad. I think I need maybe a new pencil. This one's not dark enough. Maybe make this darker. Yeah, that's better. That's better. Do I hear more customers?
No, well, I'm not showing any yet, sir. Still just me and you.
Well, what about your dog? Is your dog with us?
No, I mean, I'm sure there's quite a few of them running around here somewhere, but
They're not interested in this.
no, they don't. They're not really all that interested in dynamics.
Now, they could get interested maybe in a little piece of bacon, perhaps.
Perhaps.
Yeah. I just fed some leftover bacon to the dogs next door. They don't bark at me.
Do you have any dogs, sir? Do you have any pets?
Yeah, we have one, and she's 12 years old, but she still takes me for a walk.
Oh, well, that's nice of
Yeah.
her.
Uh-huh.
What kind of dog is it?
She's a mutt.
Oh, well.
We got her from the pound 12 years
Oh,
ago.
oh. Yeah, we have some German Shepherds and then a Pit Bull and a Pomeranian.
How wonderful.
Yeah, and then we have 2 cats.
Oh, that's great.
Yeah. And my son has a snake.
Oh, how nice.
Yeah. Yeah, it's a big snake too. It's like 5.5 foot long.
Wow. Hey,
Yeah.
Dalton has just joined us. That's good.
Yep, that's good. We have somebody else in class with us.
Yeah. Well, we're on our last week of school, and our last topic is impulse and momentum, angular impulse and momentum. So that's what we'll talk about, angular impulse and momentum. I could give you the equation for that. When more show up, we're going to go ahead and launch into this F-18.8. I don't see where it says F-18.8. Yeah, there it is. This just isn't dark enough. F-18.8. Well, let's see, what time is it? We have 4 more minutes. 4 minutes. Anyone? Hey, there's some more people. Caitlin and Eric. Yay. Does anyone have any questions before we start the fun? Oh, okay. Today's topic is angular impulse and momentum. Let me write that. But we're going to do this problem first. Topic for today, angular impulse and momentum. Uh-oh, ran out of space. Oh, well, we'll get to it. Well, if you don't have any questions, I'm going to launch into this problem here. And see, this is being recorded. You guys could watch that if you wanted to. Has anybody watched any of the YouTube programs that we've been recording? Anybody?
I have.
Tell me, I'm curious, how do you log on to the YouTube? What do you do? Do you type in YouTube?
Yeah. Or you can go to Blackboard and go to the link you posted that had your profile on it.
Oh, you could go to Blackboard and go to the link that I posted on Blackboard, and that'll get you to YouTube?
Yes.
But you could just go to YouTube.
Yes.
Type in YouTube. After you type in YouTube, then what do you type in?
I mean, you could probably, I didn't do it that way, but you could probably try to look you up on it, look up your profile.
Yeah, and I haven't done, I've just done it through Blackboard, but whenever like I did it for one class, like it still pulled up all the classes for you. Like, I mean, I don't remember which class I was actually looking at. I think maybe thermo.
Yeah.
But I could still see all the ones from all the classes right there. It was a lot easier than just going to YouTube and searching.
Yeah. Well, I was just curious. Okay, well, we're going to get started here. Let's see. Now, I asked you guys to work on this problem, and I hope you did. But let's just work it to death, shall we? Now, first we could get the moment of inertia. The way you do that is you take the mass times the radius of gyration squared. I can't do that in my head. It's too hard. So let me see what that is. 50 times 0.3 squared is, I get 4.5. 4.5 kilogram meters squared. Now that's the moment of inertia about the center of mass. But we need the moment of inertia about this point A. That's your ICZV. So here we're going to get that. That would be IG plus the mass times the distance squared between the point A and the point G. Okay, well, that'll be 4.5 plus 50 times 0.4 squared. I'm getting 12.5 kilogram meter squared for the moment of inertia about 0.8.
Hey, Professor,
Yeah.
isn't the moment of inertia equation, isn't it divided by like 2 for a circle?
Just a minute now. Yes, it is, but we don't have a disk. We don't have a circle. We have a reel or a spool. I prefer spool. And the moment of inertia about a spool is different than the moment of inertia of a cylinder.
Okay.
Are you okay with that? See, we don't have a cylinder. We have a like a fishing reel, you know, it's like two discs with a spindle in the middle.
It's a hollow center?
Yeah, it kind of got a hollow center. And
Okay.
you can't use the wrong formula. That would be bad. Okay, now this chapter 18, I think, is work energy. So you're supposed to do it with work energy. But see, we can do it with Newton's second law. Why don't we do it with Newton's second law? And then we'll do it with work energy. And then I'll show you how to do it with impulse momentum. Doesn't that sound like fun? I'm sure that.
Why, yes, it does.
Yeah, it sounds like fun. Okay, now work energy. Well, dang, you're supposed to have two. No, we're going to do Newton's second law. You're supposed to have two pictures. I don't have room to put the second picture there, but you're supposed to have two pictures, and you're supposed to put the forces in red. Here, I'll try to put the forces in red. Here goes. You're going to have a force here and a weight here. Now that weight, oh gee, it's 9.81. 9.81 times 50. I can do that. 50 times 9.81. It's 490. This is 490.5 newtons. And then see you have this normal force. That's your normal force. Now what that is will be 490.5 times the cosine of 30, which gives you 424.8. And then you have friction. And friction. I think it's going this way, but I'm not sure. Okay, I tried to put all my forces in red, like I told you guys. And you're supposed to draw another picture here. Yeah, we can squeeze it in. You got these numbers here that we're going to need, and we know what those are. But the other picture looks like this. It's going to have an I alpha and an NA. And we have to draw the hill here. Here's the hill it's on. But there, I tried to draw the second picture. Let me get a different pencil. Let me see if I can find one that's darker. I think these dry up after a while. Okay, I got another pencil now. And if you're going to use Newton's law, you could you could do this. That's Newton's second law, but it's only good if you have a fixed pivot or an ICZV, which we have. See this point A is an instantaneous center of zero velocity, and you can use this equation. So let's do it. Those two forces go through. Okay, I'm all wrong. Guys, I'm absolutely wrong. That is not the ICZV. And I'm wrong. This is. We're going to call that. Now, wait a minute. Wait a minute. Did they say there's any friction or is this thing smooth? Let me read what it says. It says F18.8. You got to find it here. Smooth. It's smooth. If you read this problem, it says it's smooth. You know what that means? There's no friction at all. If it's smooth, you can forget friction. There isn't any. All right. Dang, I just spilled all my pencils. Now, just hang on with me here. We'll get organized. Okay. Now we're going to call this point A, because that point A right there is the ICZV. See, this is slipping right here. This thing is slipping, and it's sort of unwrapping, or what's the word? It's unwrapping about A there. So I like this equation now. But now wait a minute. Wait a minute. That means this is wrong. Now we got the IG right, but the IA, if A is going to be here, this is wrong. We don't want that. Let me figure the IA. Here we go. IA will be IG plus 50 kilograms times the distance between A and G, which is 0.2 squared. All right, we're going to get the right answer for that now. Here goes, 4.5. What I had was wrong, plus 50 times 0.2 squared. It's 6.5. IA is 6.5. Now, before we go on, I made a couple mistakes, but I don't know. I think sometimes you learn more when I make mistakes, but I think we're correct now. Let's pause a minute and see if there's any questions so far. Any questions so far? We're doing F18.8. It is on page 502. We are on page 502. Is there any questions so far? Well, okay. I guess not. All right, now the sum of the moments about A. Well, you see this call this T for tension in your cable here. It goes through A. This normal force goes through A. But this gives you a moment. That gives you a moment of 490.5 newtons times 0.2 meters times the sine of 30 degrees. If anybody doesn't understand that, just speak up. We got a good crowd here. I see Ross and Sam, Julian, Gavin, Eric. And this is counterclockwise. And it's going to equal 6.5 times alpha. Okay, we're going to find alpha now. Here goes. I'm finding the angular acceleration. That's alpha. So we'll take 490.5 times 0.2 times a half divided by 6.5. I got alpha. I'm thinking alpha is 7.546, bunch of numbers there, radians per second squared. But that's not what they wanted. Let's see what they wanted. If you read this, it says, determine it. They want the angular velocity. Angular velocity when the center has traveled six meters. Okay, now this center is going to travel down here 6 meters, okay? So we can get the angle. Here's the way it works. This is called the arc length equation. You all know that. It's the arc length equation. And if you go 6 meters, 6 meters, and the R, see the R we're talking about is right here. There's your R, it's 0.2. And the theta, hey, I can do that. The angle it turns is, I think it's 30. What's 6 divided by 0.2? Yep, it's 30. 30 radians. All right, here's the equation now. The equation goes like this. Omega squared minus your initial omega, which is 0 squared, is equal to 2 alpha times your change in angle. And see, the original angle was 0, so the change in angle is 30 radians minus 0 radians, which is 30. So we know this, it's 30. We know this, it's 7 point blah, blah. So we can solve for omega. Here goes. We're going to find omega now on this problem. We're going to take 2 times 7.54615 times 30. Take the square root. Well, I'm getting 21.28 radians, which are nothings. They don't have units. I wonder if that's what they got. Now, we're going to do this a couple other ways. Now, we don't need no stinking answer book. But just for fun, we're going to look this up and see what they said. Okay. Now, you probably didn't do it this way. What I did was I used Newton's second law. And now we'll see if we got that right. This was problem F18.8. And they said F18.8 is 21.3. And I did this wrong. It's not nothings. This is, the theta is nothings. This is nothings. But this is nothings per second. It's radians per second. So the correct answer will be, and what the book says is 21.3. The book says omega is 21.3 radians per second. Yay! Yay! We got what the book got. Okay, now let's do it a different way. That was solving it with Newton's second law. Now we're going to solve it with work energy. Now that's chapter, I don't know, is it chapter 19? No, it's 18. That's what we were supposed to do. We were supposed to solve this with work energy. So let's do it, shall we? I just need some room here. But before I erase some stuff, did you have any questions on how to do that with Newton's second law? Well, nobody said anything. Okay. Well, let's do it with work energy. I need this room now. So we're going to have to say goodbye to Newton's second law. Let's keep that answer, though. See, we solved it, and we got 21.28 for our answer using Newton's second law. Now let's solve it with work energy. Okay, now this is the equation for work energy that we all know and love. That's it. Now we're going to figure out the work done. Well, the normal doesn't do any work because it's moving down the hill, and the normal is perpendicular. And to do work, you've got to have a force in the direction of your motion. But that force is always perpendicular. I'll take this sweater off. It's getting too warm in here. Well, that normal doesn't do any work. And this tension in this cord doesn't, because it's like rolling. It's like rolling. See, rolling doesn't do any work because there's no friction. There's no motion. There's no motion of the cord relative to the spool. Did they call it a spool or did they call it a reel? Let me see what they called it. They called it a reel, kind of like a fishing reel. You've heard of rods and reels when you go fishing. You know, a reel is one of those deals where you crank it up. You know, it's got the fish line on it. But see, there's no motion of the fish line here with the reel. It's just unwinding. The only thing that does any work is this 490.5. Now, if it goes 6 meters down the hill, that means it drops down 3 meters. Now, let me review something about 30, 60, 90 triangles for you guys. In case you're rusty, the way it works is if you have a 30-degree angle, and this is 6 meters, Then this is 3 meters. I think maybe I drew that a little too big. Let's try to do it better. Did you know that the small side on a 30, 60, 90 triangle is 1/2 the longest side? Hopefully you know that. If you don't know that, maybe you better switch to psychology. Maybe it's time. But I'm kind of teasing. I know you all know that. It's a 30, 60, 90. So this thing drops 3 meters, and we can figure out the work done by gravity, right? Right, Mr. Griffin. Okay, here goes. The work done by gravity is going to be the 490.5 newtons times 3 meters. That's it. We're done. That's the only force that does any work. Let me erase this 30, 60, 90 triangle. And that's going to equal, in this case here, since you have an ICZV at A, it's going to equal 1/2 the moment of inertia about A times omega squared. Well, we know what the moment of inertia about A is. It's 6.5. We figured it out. I think I did it wrong, had the wrong A there for a while, but we're okay now. All right, I'm going to plug that in and get it. Here goes. Take 490.5 times 3 times 2 divided by 6.5. Take the square root. And here's what I'm getting for your angular velocity when it rolls down the 6 meters. I'm getting 21 point, rounded off to 28 radians per second. Now let's compare that with what we got with the Newton's second law. Well, Shazam, you know what? That's the same answer we got with Newton's second law. Which do you like the best? Which method do you like the best?
Work energy.
It's easier, yeah. It's easier. Now, let's get the time it takes. I bet we can get the time. We're going to solve for the time it takes to go from rest, it starts at rest, to roll down the hill and have this angular velocity. Well, there's an equation that goes like this. Boy, that's pretty easy. If this is 21.28 radians per second, and alpha is, oh gee, I erased it. Is anybody taking good notes? We got alpha and I erased it. What is it? Somebody's got to help me because I erased the alpha. Somebody, anyone, hello class, anybody awake out there?
I think the alpha was 7.54615.
546. Thank you so very, very much. That would be radians per second squared. Now, who was that just helped me? Who was that?
Sam.
Sam. Yeah, the Sam that laughs at my jokes, that Sam?
Yes. Oh, man.
Oh, good going, Sam. Proud of you. Okay. Now we're going to find the time. Here we go. Well, that's pretty easy to do. Let me do that. We're going to find the time it takes. 21.28. Okay. Then you divide by 7.546. 5, 4, 6, 1, 2. Okay, I got an answer for the time of 2.82 seconds. Here, let me write that over here. Maybe I should write that alpha too that Sam gave us. We might need that again too. 7.546. And then the time we think is 2.82 seconds. Okay, now that was a lot of fun. And we did the problem 2 different ways. See, we don't need no stinking answer book. If you could do the problem 2 separate methods and get the same answer, hey, we know we're right. Now we're going to do it a third way with a third method called the impulse momentum method, angular impulse momentum method. But we did it with work energy. And before we go on, does anybody have any questions about the work energy method? I'll wait a tiny minute if you have a question. Well, nobody said anything. Well, let me give you these equations for work energy, and then we'll do that way. I've got them written down here someplace. Totally organized, as always. I thought I did. Dang, I can never find anything. I'm going to get organized one of these days, guys. Hey, while I'm at it, some of you are missing that example 1612, where you had the crankshaft and the connecting rod and it. Let me erase this and talk to you about that, and then we'll get to these wonderful equations. I'm going to have to erase this. I hope you got good notes there. We did it with work energy. We got the same answer. We're going to do it a totally different way now. But first, I need to tell you that we did example 1612. I know you might remember it. It's on page 366. And I think the example in the book has 45 degrees. Do you remember they had a crankshaft that was 0.2 foot, and then 0.75 foot. Does this ring any bell? And a piston up here, and this angle here in the book was 45 degrees. And then I asked you to do it with the angle there of 30 degrees. And then I think I asked you to do it for 20 degrees. Let me ask somebody if they remember that. Daniel, unmute, Daniel. Do you remember working these problems here, Daniel? Daniel, Earth calling Daniel.
I remember.
Daniel remembers. Well, I was looking at my grade sheet thing here, and some of you have not done that. Now, a lot of you have. Like, for instance, Tyler, he didn't do it at 30 or 20. Kristen, I do not have you down for the 20 and 30 degrees.
I did that. You graded it. You emailed me back.
What did I give you?
I think it was a 3. I messed something up. I'll have to find it though. Hold on. I'll look for sure.
See if you can find it.
Yeah, let me check my emails and
Yeah.
where you emailed me back.
Okay, now, Julian, I don't know if Julian's with us today. I don't see, Julian's not with us. He didn't do it. I don't have anything for him. Kevin, is Kevin on he's not with us today. Kevin didn't do it. Gavin Jackson, I bet yeah, there you are. Gavin, I don't have anything for you 20 or 30 degrees. Did you do that? Gavin Jackson, Earth calling Gavin Jackson, unmute.
Yeah, I'm pretty sure you graded mine as well.
Dang, do you know what you got?
I'm not sure. I can look at my emails though.
Find out before we close today, and I'll put them in the book here. Sam,
All right.
Sam, the guy that helped me here a little while ago. Did I ever give Sam a thank you point? Shouldn't he get a thank you point for thank you point up here for Sam? Sam, I don't have anything down for the 20 or 30 degree. Did you do that?
Yeah, I remember doing it.
Dang.
Okay, you gave us the first one. It was like we did it at 30 and 60, and
Yeah.
you gave me a 3 on that one because you said my angles were off.
Oh,
And then we did another one after that where we did it at 20 degrees, and
Yeah.
you gave me a 4 on that one.
you are now recorded.
Thank you.
In my
Maybe we should all just get 4s.
I found the email and he said that I got a 4 on it.
who's that talking?
Gavin Jackson.
You got 4 on both of them?
Wasn't it just the example 1612?
Yeah,
Or
but
was it?
I gave you 30 degrees and then I gave you 20.
Oh, yeah. Yeah.
You got 4 on both of them?
Yes.
Okay, I got it for you there. Sam, what about you? Don't know yet.
I don't know yet.
Okay, what about Alex? He's probably not listening.
No, I'm here.
Alex, did you do those at 20 and 30?
I think I did, but I probably did them wrong.
Well,
I'll just be honest.
I love honesty. Honesty is it's priceless. It really is. Sam, let's put 3s in there for now. And if that's not right, you email me. You got it? What about my friend Taylor? I don't think she's on here today. I don't see her. She's not on here. How about my friend Dalton? Now wait a minute. Dalton did it at 20. He got a 3, but I don't have anything here for 30. Dalton, did you do it at 30?
Yeah, I turned it in and I turned 2 homeworks in and
Yeah.
you gave me a 4 points on one of them. You didn't specify which one.
Well, you got a 3 on the other one, so it's got to be a 4. Now, how about Gavin Shepard? Gavin Shepard, did you do the? I got 4 for 30. Did you do the 20 degree thing? Earth calling Gavin Shepard.
I don't think he's here today.
Oh, he's not here. What about Mohammed? Mohammed, I have a 4 for the 30 degrees, but nothing for the 20 degrees. Did you do the 20 degrees, Mohammed? No answer. Maybe he's not tuned in. Cameron, is Cameron here? Cameron, Earth call. Yeah, you're here. Cameron, I got, I'm not going to mention what you got for the 30 degrees, but did you do the 20 degrees?
Yes, I believe so.
You don't remember what you got?
No, I do not.
Look, I'm going to put a 3 in here, and if that's not right, you contact me.
Okay, I will.
Allison, I don't have a grade for your 30 degree thingy. Did you do 30 degrees, Allison?
Yeah, I'm pretty sure I got a 3.
Put that in. We got that. William Vang, is William here? William, Earth calling, he's not here. Brandon York, important guy. He got a 4 points on the 20 degrees, but nothing on the 30 degrees. Brandon, are you here? No, he's not tuned in. Hey, but there's Julian. Julian tuned in. Julian, I don't have anything for 30 or 20. Do you remember doing those, Julian? You know what we're talking about? We're talking about this example 1612. And I don't have any grade for you for the homework.
I didn't do it.
Honesty is so good. Julian, turn something into me on I think those are Blackboard problems. And I'll give you some points, okay?
Alrighty.
That's good. I'm glad we did that. And here's my reason. I'm going to put one of these on your final, but I'll change the angle. But see, if you can do it at 45 and 20 and 30, you can do it at whatever angle I ask, can't you? Oh, yeah, yes, we can, Mr. Griffin. Well, I'm going to put it on the final. So I would advise you to study that so that you can get your points on that on the final. That'd be good. Okay, now back to our problem.
Hey, Mr. Griffin.
Yeah, I'm
I,
listening.
I looked through my emails and I cannot find where you replied to me. I can find where I sent.
Yeah,
Oh, I find where I sent them to myself because I had to because weird reasons.
good
But
for you. Yeah. Now who is
I
it?
can't find your reply on them or what score you gave me for them.
Who's this that's talking?
Sam.
Okay, Sam. Sam, I forget your last name, Sam.
Moffat.
Yeah. Sam, I'm gonna put 3s in there for both of those. And if you're not happy, you resubmit those. Okay.
Okay.
And I'm gonna give you some equations now. And we're gonna solve this same problem. We're gonna do the F18.8, but we're gonna do it with impulse momentum. Angular impulse and momentum. Angular impulse and momentum. It's another method. See, there's Newton's second law, there's work energy, and there's impulse momentum. Now here's some equations. To review, we've studied regular linear impulse and momentum. And the equation for that, here, let me give you that equation. The equation for linear impulse momentum goes like this. And hopefully you remember. This term is called linear impulse, and this term is called the change in linear momentum. But see, we're going to study the angular impulse momentum. This is chapter 19, I think. Is it chapter 19? Yeah, it's chapter 19. Now, the way it goes is like this. Where this thing here, that's called angular impulse. See, that's called linear impulse. And can you read my writing? That's called angular impulse. Now, this is the change in linear momentum, and this is the change in angular momentum. Okay, now there's a number of equations for that. Sometimes they write this like this. And sometimes they write this like this, where L is the book symbol for linear momentum, and H is the book symbol for angular momentum. Okay, and here's our equations. This is the angular momentum about your center of mass. but there's a couple of other equations that go like this. This is your angular momentum about another point that's not the center of mass. And there's a third equation that goes like this. I'll give you these equations, then we'll do our problem. Those equations are awfully reminiscent of some other equations that we've studied, namely this one here. The sum of all the momentum, the sum of all the moments about a point other than the center of mass is equal to we've had this. And there's a second equation that looks like this. Now these are called moments of forces, and these are called kinetic moments. I've told you about that. They're kinetic moments. Just like with Newton's law, F equals ma, this is called forces acting on your body, and these are kinetic forces. MAs are kinetic forces. These guys here are kinetic moments. Now the beauty, I wrote those because we've seen those before, but don't these look reminiscent of those? They sure do. Do you remember there's a special case, if you have an ICZV, you can get rid of this because a fixed pivot or an ICZV doesn't have any acceleration and it doesn't have any velocity either. And so you get this wonderful equation here. But be careful, this equation has a skull and crossbones. It's only good for fixed pivots or ICZVs. So now I have reviewed with you all those wonderful equations that you need. And now I'm going to erase that unless you have a comment or question. And we're going to do this problem now with impulse momentum. But first, do you have a comment or question? Okay, well, I'll ask you something. Let's see if anybody listened to me. I want you to know the names of this stuff. Do you see this H with a little G here? That stands for something. I'll pick on somebody. Caitlin, I never pick on you. That's a lie. I pick on you all the time, don't I, Caitlin? Unmute, Caitlin, and tell me the name of that guy right there, that H with a little G under it. What's the name of it, Caitlin?
Is it the angular impulse?
No, no, no. The angular impulse term is this one, Caitlin. That's the angular impulse. But thank you for trying. Thank you for trying. Well, try again, Caitlin. What is the name of that? See, it goes over here. See that H there? It's on the right-hand side. See, this is the left-hand side. Those are the angular impulses, and these are the
Angular momentums?
Oh, you were so close. It's an angular, say again?
Momentum?
Yeah, that's it. That's angular momentum. That's what that is. Good going. I want you to know the names of all that stuff. Okay, well, that's enough highfalutin theory. Let's work our problem now. You guys could read the book too. That's another thought. Yeah, you could read the book. Probably wouldn't hurt. Okay, so we're going to work this problem with angular momentum now. And here's the equation we're going to use. Now this is final minus, you got that wrong. This is final minus initial angular momentum. That's what Caitlin told us a minute ago, that this stuff over here on the right is called angular momentum. Now this thing here is angular impulse. Okay, well, let's get that. What are the moments acting at A? Well, let's see. Well, the tension goes through A, so that doesn't give you a moment. The normal force goes through A, that does, but this one does. This 490.5 newtons times 0.2 meters. But since it's not acting perpendicular, you have to multiply by sine of 30. I'll explain that better to anyone that is a little bit, what happened? So wait a minute.
The camera's frozen, isn't it?
Oh no. What am I supposed to do to get this thing stop video? I don't want to stop video.
Just stop it and then hit play again.
Oh, gee. I think I pushed the wrong button here, guys. But you're still hear me. You guys can still hear me.
Yeah, for now.
Okay. We were doing so well. I wanted to show you that equation with another method. You're still on board. It froze. Start video, it says. Okay, I clicked on it. It should start. It's not.
Are you using a webcam or something external?
Hey, the little light went off on my camera. Come on now, camera. It's recording, it says.
Yeah, but I don't think it's recording. It's only recording the screen right now. It's not recording output.
No, it's not recording. Oh, gee.
Is it a camera that's built into the device you're using?
Yeah, it's built into the computer, this laptop.
Okay, that's not good.
Oh no. It's supposed to have a little light that comes on up there by the camera.
Yeah.
Start. I keep clicking on start video. Cannot start video. Failed to start the video camera. Please select another video camera in settings. What do you mean another video? I only have one video camera.
We probably just fried it. The camera probably just died, so you're probably gonna need to get a new one.
Oh no.
Great.
What am I gonna do? My worst nightmare happened. I was going to show you that we were going to get the same answer. I was doing so good. And then it just froze. And then my class at 1 will be out of whack.
Yeah, how will we know if you got it working again for that class? Just try to log in, and if you're not here,
Yeah, try to log in, and if I'm not here, I'm not here. I don't know.
okay. All right, I was just curious.
This says share screen. That doesn't help much. I don't know what that does.
Let me think.
Share.
Hello?
Hello.
Oh, yeah, that's our, I was trying to figure something out. Never mind.
My camera just quit working. Now wait a minute. This says stop recording. I don't think I want that.